Every single year across the United States, farmers chop and pile up about 128 million tons of corn silage. That number came from roughly 6.3 million acres of harvested corn, all of it fed to the nation's dairy and beef herds. But here's the part most people never see. Most people picture a cow eating chopped corn out of a feed bunk. What they never picture is the quiet fight that happens long before that. A fight against a single enemy: oxygen. Because chopped corn is not feed yet. It is a huge wet pile that can either turn into rich, sweet cattle food or rot into waste that costs a farm real money. The difference between those two outcomes is decided in just a few hours. It is decided by weight. Today we're stepping inside a working corn silage bunker to see how the whole crop is chopped, hauled, layered, and crushed under one of the heaviest tractors on the farm, the John Deere 9RX 710. We'll follow the crop from the field to the sealed pile, and we'll find out why the heaviest machine on the lot is the one that saves the most feed. Let's start where all of it begins. In the field, with a corn plant that is not quite ready. Corn silage is the whole corn plant. Not just the ears, not just the grain. The stalk, the leaves, the cob, and the kernels, all of it chopped fine and stored wet on purpose. That last part surprises people. Most crops get dried down for storage. Silage is the opposite. It has to stay wet so it can ferment, the same way sauerkraut or pickles ferment in a jar. That fermentation is what turns the pile into stable feed that keeps for months. But the plant has to be caught at exactly the right moment. Too wet, and it ferments poorly and leaks. Too dry, and the air can't be pushed out. The target is 30 to 35% dry matter. That means the plant is still 65 to 70% water when it goes into the pile. Farmers don't guess at this. They test it. A common method is to take a fresh-cut sample and dry it in a microwave or a small oven called a Costa tester, then weigh what's left. The plant loses moisture slowly, about 0.5% of dry matter per day, so a farmer watching a field knows he has a narrow window. Miss it by a week and the whole chemistry of the pile changes. This narrow window is further complicated by regional and climatic variations. In the upper Midwest, for example, the growing season might offer a more predictable moisture decline, allowing for precise scheduling. However, in the southern plains, hotter, drier conditions can accelerate moisture loss, shrinking that ideal harvest window to just a few critical days. A wet fall can also delay harvest, pushing the crop past its optimal dry matter percentage and increasing the risk of poor fermentation. Farmers must constantly monitor weather patterns and plant maturity, adapting their harvest timeline to ensure the crop enters the bunker at its absolute best. It is a constant negotiation with nature, where timing is everything. When the crop hits that target, the machines roll, and the first machine is the one that does the cutting. The forage harvester is a giant. It drives straight into the standing corn and swallows entire rows at once. Inside, a drum spinning at high speed slices the whole plant into tiny pieces. Farmers set what's called the theoretical length of cut, and for corn silage, it runs between 3/8 of an inch and 1/2 inch. When a kernel processor is fitted, that stretches up to about 3/4 of an inch. That processor matters. It's a pair of rollers that crack every kernel and smash each cob into 6 or 8 pieces. Whole kernels would pass straight through a cow undigested. Cracked ones release their starch. So the chop does 2 jobs at once. It breaks the grain open for the animal, and it makes the pile pack tighter later. Finer chop is denser chop. Small pieces nest together and leave fewer air pockets. Remember that, because air is the whole problem we're trying to solve. Now the crop is chopped, and the race begins. A modern forage harvester is fast. It can deliver 50 tons of chopped corn per hour on a modest operation, and on a big custom crew, 150 to 200 tons per hour. Trucks and wagons line up beside the harvester, catch the stream of silage as it fires out the spout, and haul it to the storage site. That site is usually a concrete bunker with tall sidewalls, or a drive-over pile built straight on a pad. Truck after truck backs in and dumps its load, and this is exactly where farms get into trouble. The harvester is a fire hose. If the chopping crew is delivering 150 tons an hour, and the packing crew can only crush 80 tons an hour, the pile grows faster than it can be squeezed. Loose silage, full of trapped air, gets buried under the next load before it's ever been packed. That trapped air is a slow leak of money, and nobody sees it happen. The pile looks fine on the outside. It rots on the inside. So how does a farm keep up? How does it match the crushing to the delivery? That's the core of the whole system, and it comes down to one simple rule. If you enjoyed this deep dive into corn silage so far, make sure to like, subscribe, and hit the bell so you never miss our next exploration into the giant industries that quietly power the modern world. Now, back to the pile and the rule that decides whether it survives. Extension engineers who study this call it the 800 rule. The idea is plain. For every ton of silage delivered per hour, you need about 800 pounds of packing weight rolling on the pile. Do the math and it gets real fast. A crew delivering 50 tons an hour needs roughly 40,000 pounds of packing equipment. That's 20 tons of tractor. Push the delivery up to 100 tons an hour, and now you need about 80,000 pounds, 40 tons of iron, crawling back and forth without stopping. This is why the tractor is the star of the whole operation, and this is why farms reach for something like the John Deere 9RX 710. It is one of the largest tractors John Deere builds, and on a packing job it gets even heavier. Crews bolt on extra weights, front and rear. They fill the tracks and frame with added ballast. A machine like this can be loaded past 100,000 pounds for the job. It doesn't need to be fast, it needs to be heavy, and it needs to keep moving. But weight alone isn't the whole trick. It's how that weight is laid down. While the packing tractor works, another tractor called the push-up tractor is spreading the fresh silage. It doesn't dump it in a big heap. It spreads it in thin layers, 6 to 12 inches at a time, building the pile up as a long ramp or wedge. This wedge shape matters. It gives the packing tractor a slope to climb and pack against, and it lets each new layer sit thin enough to be fully crushed before the next one lands on top. Thin layers pack faster and denser. There's an old line among silage crews that sums up the whole job. When you think you're done packing, pack that much more. Because loose silage always looks packed from the seat. It rarely is. So the packing tractor climbs the wedge, slow and steady, and drives the air out layer by layer. Now here's where it gets interesting, because the way that heavy machine grips the pile changes everything. There's something crews call the wall effect. On a big track machine, only the outside edges of the tracks reach the very edges of the pile. The center of the machine crushes the center of the layer beautifully, but the sides, especially near the concrete walls, get less pressure. That's why operators drive tight patterns, working the edges on purpose, overlapping passes, and running slow. Speed is the enemy here. A tractor rushing across a layer bounces and skips. A tractor crawling puts its full weight into every square foot. The measure of success is density. The target is about 15 pounds of dry matter per cubic foot. As fed, with the water still in it, that's 44 pounds or more per cubic foot. Crews check it by coring the pile and weighing samples. And the density number is not just a bragging point, it is the whole game. Here's what happens when you miss it. Back in 1992, a researcher named Ruppel put real figures on the cost of loose packing. At a density of just 10 pounds per cubic foot, the pile loses about 20.2% of its dry matter over 180 days. That's a fifth of the feed, gone. Bump the density up to 15 pounds, and the loss drops to 15.9%. Push it to 18 pounds, and it falls to 13.4%. Every pound of density you add saves feed that would otherwise rot away invisibly, and the studies keep proving it. In one 7-year investigation of 189 bunkers across 75 farms, densities ran all over the map, from a poor 8.4 pounds per cubic foot to a strong 17.2. The same study found the losses weren't even. The top third of a bunker lost 11.7% of its dry matter, while the bottom lost only 5.6%. The front of the pile, the feed face, lost more than the rear. So the parts hardest to pack, the top and the edges, are exactly the parts that rot first. Now put a dollar sign on it, because that's what farmers actually feel. At $40 per ton as fed, a pile packed to only 13 pounds per cubic foot bleeds about $7 per ton to dry matter loss. Pack it tighter, to 17 pounds, and that loss drops to around $5.50 per ton. That gap doesn't sound like much on 1 ton. Multiply it across thousands of tons in a single bunker, and it becomes the difference between a good year and a thin one. And here's the hard truth from the surveys. Only about a quarter of bunkers actually hit that 15-pound target. 3 out of 4 farms are leaving feed and money in the pile. This is exactly why the upfront cost of a machine like the 9RX 710 pencils out. A tractor that heavy, packing that hard, can do the work of several lighter tractors and the operators who'd run them. It builds a denser pile, which means less spoilage, which means more of the crop actually reaches the cows. The iron is expensive, the rot it prevents is more expensive, but the packing is only most of the fight. There's one more step, and skip it, and everything else was wasted. Once the bunker is full and packed to the top, the crew has to seal it. Plastic sheeting goes over the whole surface, up the sides and across the top, tucked tight against the walls. Then that plastic has to be held down flat, because wind and gaps let air sneak back in. Crews weight it with tires laid edge to edge, touching each other so there are no bare spots. Some use sandbags or long gravel-filled bags laid in rows. Many farms now add an oxygen barrier film, a thin sheet that clings to the silage surface under the main tarp and blocks air far better than plastic alone. Why go to all that trouble for a top layer? Because the numbers on an uncovered pile are brutal. An uncovered bunker can lose 75% of the dry matter in the top 10 inches. The next 10 inches below that lose about 25%. For a bunker measuring 30 feet wide by 100 feet long, that top layer loss adds up to roughly 50 tons of corn silage gone. 50 tons rotted off the top, simply because a tarp was skipped or laid loose. All that chopping, hauling and packing, undone in the one step that costs the least. With the seal on, the pile goes quiet. Fermentation runs sealed for at least 3 weeks. In that dark, airless space, natural bacteria turn the plant sugars into acids, and those acids pickle the pile into stable feed. When it's ready, the crew opens one end, the feed face, and begins feeding out. A good, dense face stays firm and doesn't heat up in the air. A loose one crumbles and spoils as soon as the oxygen hits it. The process of fermentation in silage is a complex, multi-stage biological transformation. It begins with a brief aerobic phase, lasting only a few hours, where trapped oxygen is consumed by plant respiration and aerobic microorganisms. This initial phase is critical to remove as much oxygen as possible. Next comes the main event, the fermentation phase. Here, anaerobic bacteria, primarily lactic acid bacteria, take over. These microorganisms convert plant sugars into organic acids, predominantly lactic acid. This rapid production of lactic acid drives down the pH of the silage, ideally to a range of 4.0 to 4.2. A fast and efficient pH drop is more important than the final pH itself, as it quickly inhibits undesirable spoilage organisms. If oxygen remains or the fermentation is slow, less beneficial bacteria can thrive, leading to the production of butyric acid, which gives silage a rancid smell and reduces palatability. Clostridial spoilage can occur in very wet silage, consuming lactic acid and producing butyric acid and ammonia, further degrading feed quality. Molds and yeasts can also proliferate if air penetrates the pile, leading to visible spoilage and mycotoxin production, which are toxic to livestock. The entire stability of the pile hinges on this precise microbial activity. To assist this natural process, many modern operations employ bacterial inoculants. As the corn is chopped, a fine mist of these specialized bacteria is sprayed onto the crop. These inoculants introduce a high concentration of beneficial lactic acid bacteria, accelerating the fermentation process and ensuring a rapid pH drop. Homolactic strains primarily produce lactic acid, driving a quick, efficient fermentation. Heterolactic strains produce a wider range of acids, including acetic acid, which can improve aerobic stability when the silage is exposed to air at feed-out. Some farms also use propionic acid treatments, particularly on the feed face, to further inhibit mold and yeast growth and prevent heating. These additives are a targeted intervention, a biological assist to a massive industrial system, ensuring maximum feed quality and minimizing waste. Once the pile is sealed and fermentation is complete, the next critical phase begins: feed face management. When the bunker is opened for feeding, the exposed surface, known as the feed face, becomes vulnerable to oxygen. A dedicated machine, often called a defacer or facer, is used to remove silage. Unlike a bucket loader, which can tear and loosen the feed face, a defacer shaves off a clean, smooth layer. This precision prevents oxygen from penetrating deeper into the pile, which would lead to aerobic spoilage, heating, and mold growth. In warm weather, farms must remove at least 6 to 12 inches from the entire face each day to stay ahead of spoilage. If the feed-out rate is too slow, the exposed silage heats up, molds, and loses nutritional value, undoing all the packing and sealing efforts. It is a continuous battle against the air, even after the pile is opened. Finally, the sheer scale of these operations introduces significant safety considerations. Right after filling, silage bunkers can produce dangerous levels of nitrogen dioxide, a toxic gas heavier than air that accumulates in low spots. This gas, often visible as a yellowish-brown haze, can be deadly, and crews must exercise extreme caution, ensuring proper ventilation and avoiding entry into confined spaces without monitoring. Additionally, the massive walls of concrete bunkers pose a collapse hazard if not properly constructed and maintained. When feeding out, there is also an avalanche risk if the feed face is undercut, potentially trapping workers and equipment. These are not just agricultural processes, they are industrial systems with inherent dangers that demand rigorous safety protocols and constant vigilance from every member of the crew. If you're enjoying this look inside the corn silage system, make sure to like, subscribe, and hit the bell so you never miss our next exploration into the giant industries behind the food we eat every day. There's one more part of this story worth telling, and it's how big this quiet system really got. Corn silage has been made in one form or another for well over a century, but the scale it runs at now is new. Back in 2013, US producers put up 118.2 million tons of it. The very next year, 2014, that jumped to about 128 million tons across 6.3 million harvested acres, a record at the time. It didn't stop there. By 2023, US corn silage production climbed past 130 million tons. That growth tracks the growth of large dairies and feedlots, operations feeding thousands of animals a day that need a steady, cheap, homegrown forage they can store all year. While bunkers and drive-over piles dominate on large dairies and feedlots, they are not the only method of silage storage. Historically, upright tower silos were common, offering excellent oxygen exclusion and a smaller footprint, but they are expensive to build and slow to fill and empty. Another option is the silage bag, long plastic tubes that can hold hundreds of tons of silage. These are flexible and cost-effective for smaller operations or for storing specialty forages. However, they are prone to rodent damage and require careful management to avoid tears. Bunkers, despite their larger footprint and the intense packing effort required, remain the preferred choice for massive operations due to their unparalleled capacity and the speed at which they can be filled by multiple trucks and packing tractors simultaneously. The cost per ton of storage is also significantly lower, making them the most economically viable option for handling the sheer volume of feed required by thousands of animals. Behind every one of those tons stands a chain of machines and decisions most people never think about. The whole crop caught at 30 to 35% dry matter, the harvester chopping it fine and cracking every kernel, the trucks racing loads to the pad, the push-up tractor spreading thin 6-inch layers, and the 40 tons of iron crawling back and forth on top, driving out the air one pass at a time. This massive logistical dance is often orchestrated by custom harvesting crews. These specialized teams arrive with their own fleet of forage harvesters, trucks, and packing tractors, charging farms by the acre or by the ton. A typical custom crew for a large operation might deploy 2 or 3 harvesters, each requiring a constant rotation of 5 to 10 trucks or wagons to keep pace. The coordination is precise. Trucks must arrive just as a harvester's wagon is full, minimizing downtime in the field. This logistical ballet extends beyond the field. Each truck's route to the bunker must be optimized to prevent traffic jams and ensure a continuous flow of material. Communication between the field crew, the transport drivers, and the packing crew at the bunker is constant, often using two-way radios to make real-time adjustments. Any breakdown in this chain, whether a flat tire on a truck or a mechanical issue with a packing tractor, can create a bottleneck that slows the entire operation, allowing valuable time for oxygen to infiltrate the unpacked silage. The cost of hiring such a crew, which can run into thousands of dollars per day, is a direct investment in speed and efficiency, ensuring the crop is harvested and packed at its peak. It is an intricate system of moving parts, all synchronized to beat the clock and the elements. It is farming. It is logistics. It is food engineering. It is a circular feed system where a plant grown on the same land is stored, fermented, and fed back to the herd that helps grow next year's crop. And the whole thing turns on a rule most shoppers have never heard of: 800 pounds of tractor per ton per hour. and a target most farms never quite reach, 15 pounds per cubic foot. The cows will never know the difference, but the farm will, because the tons that never reach the feed bunk, the fifth of the pile lost to a loose pack or a skipped tarp, were decided in the few hours it took to crush that silage down. The heaviest tractor on the lot isn't there for show. It's there because weight is the only thing that beats the air, and in a 30 by 100 foot bunker, the gap between a full one and one that's quietly rotted 50 tons off the top comes down to how hard and how slow that machine was willing to roll.